So today we're going to be looking at collisions, momentum and energy. So in physics, a collision refers to a situation where two or more objects come into contact with each other. One can be stationary, the other moving, or both can be moving. Collisions happen in everyday life. A special type of collision is an explosion, and this is not necessarily when something blows up. So explosions are when two objects, so we have two objects here and the objects here, and they push away from each other by exerting a force, so they'll maybe bounce together. Or a good example would be if you had a gun and you've got a bullet comes out of your gun in this direction, there's going to be a repulsion in that direction. That's an example of an explosion. Or another one would be a rocket blasting off into space. You've got your rocket going upwards, and you've got the expulsion gases coming down the way. So that is an example of explosive collisions. When we think about collisions, we have to consider momentum and energy transfers. We're going to look at momentum first. So let's consider the scenario. So when you do momentum, when you do any problems with momentum, do little pictures for before and after, and that helps you understand what's going on. So we've got a trolley, and it has mass 2.5 kilograms and a velocity of 6 meters per second. So it's going in this direction. And we've got a block, and that has mass 1.5 kilograms and velocity 0 meters per second. After the trolley and the block move off together with a mass of 3.75 meters per second, and obviously the mass will be the combined mass of both of these. So the equation for the sign for momentum is P, small p, and it's P momentum is mass times velocity, where mass is in kilograms, velocity is in meters per second. So our units for momentum are kilograms meters per second. There is no specific SI unit for momentum. It's just the messy looking kilograms meters per second squared. Not squared, meters per second, sorry. So in momentum, we have the principle of conservation of momentum. So the momentum before equals the momentum after. So in this situation, the momentum is going to be the 2.5 times 6 plus 0, because it's not moving, so there's 0 momentum, which gives us a before momentum of 15 kilograms per meter squared. And the momentum after is going to be equal to, well, the combined mass works out at 4 times 3.75, and if you do that, it is 15 kilograms per meters squared. And we can you can apply that principle in any type of collision. Things to note: momentum is a vector. So direction matters. And when you're doing your when you first start doing your problems, when you're considering your before and after, you need to decide what is going to be the positive direction. And let's look at a wee example for that just now. So here we've got our before. We've got some mass in this direction and some other mass coming in this direction, and the mass is 5 kilograms here, and the velocity is 4 meters per second. And this mass is 2 kilograms, and this velocity is 6 meters per second. So we're going to define, we'll just write it over here, direction as this way, positive. So the momentum in this situation is going to be 5 times 4 plus 2 times, now it's going to be minus 6 because that velocity will be negative. So that's going to be 20 minus 12, which is going to give us a momentum of 8 kilograms meters per second. Now, after the collision, we want to find out what is the velocity going to be. So we know after what is the combined velocity. So we know they're going to, these two things are, these two masses join together and they go off in some direction. So the mass is now 7 kilograms. I've drawn it as one kind of lump. So we know that the momentum must be 8 because P equals mv. The mass is now 7 and we want to find out v. V would be 1.14 meters per second. And because of the maths here, we have, we know it's moving in this direction, it's not going backwards. Now, we've looked at momentum, now we're going to look at the energy. Now we know total energy is always conserved. So let's look at a little example of what's going to happen to the kinetic energy in this system. So this has got mass 2.5 kilograms and it's got a velocity of 6 meters per second. And this has a mass of 1.5 kilograms and it's stationary, so V is 0. So let us and so this is before. Immediately after the collision, the objects now move off together. That might be stuck together. They move off with a velocity of 3.75 meters per second. That we know that the combined mass of them will be 4 kilograms. So the kinetic energy before is half mv squared. Now let's note here the v is a vector. So if it's a negative, say it was going in the opposite direction, in the negative direction, that negative is cancelled out because we're squaring it, because kinetic energy is a scalar quantity. It's not a vector. So let's work out the kinetic energy of this system before. So it's going to be half times the mass 2.5 times 6 squared, and that's going to give us 45 joules. And this is from this little trolley. This lump here has no velocity, so it has got 0 kinetic energy. Let's look at the system after. Half mv squared again, half times 4 times 3.75 squared, and that gives us 28 joules. But this is less than this. Kinetic, so this is important, kinetic energy is not usually conserved. The overall energy in this system is conserved, but there's lost energy. And that energy will be lost with either sound or heat. If you were to look at this with a slow motion camera, but it was very high resolution, you would see that when the collision happens, there's going to be like a little kind of deformation. The trolley will hit in here. Oops, that's a terrible trolley. And you'll see a deformation of this will be deformed a wee bit, and this deforming of the materials at the collision actually will be an absorbing of some of that energy. So this is a place where energy is lost. When we have collisions where kinetic energy is not conserved, are called inelastic. So that's important to remember that. If we have inelastic collisions, we can also have elastic collisions. So this time we're going to consider some mass moving in this direction. The mass is 3 kilograms and the velocity is 5 meters per second, and it's going to collide with this mass here, which also is 3 kilograms, and velocity is 0. So this is the before and this is the after. This is still mass 3 kilograms, and this is velocity 0. So what's happened is this has collided, and this has stopped moving, and this has started to move. This is still mass 3 kilograms, and we want to know what this velocity is. So let's look at the momentum here. So momentum is always conserved. It's a law of physics, it's always conserved. So the momentum before, P equals mv, so we're going to have the mass 3 times 5, and that's going to have 0 momentum, so that gives us a momentum of 15 kilograms per kilograms meter squared. And the momentum after is mv, so this must be the same. The mass of the one that's now moving is 3. We don't know the velocity, but this is now, our first mass is stationary, so that's got 0 momentum. So the velocity is 5 meters per second, which was the same as this. you can see where this is going. So the kinetic energy of this system, half mv squared, half times 3 times 5 squared, is going to give us 37.5 joules, and this has got zero kinetic energy. And the kinetic energy after, half mv squared, again, is going to be half times 3 times 5, which is 37.5 joules. So this shows us that in an elastic collision, kinetic energy is conserved. Now, in reality, elastic collisions don't really happen. They only would really happen maybe between charged particles, where you've got an electrostatic repulsion so that they don't actually touch. But when you get when two objects touch, you're always going to have a transfer of some other kind of energy. So although we defined elastic collision as where kinetic energy is conserved, the reality is they don't really happen, apart from a few very specific occasions. Or maybe you're sometimes perhaps with if you had an air track and you were colliding moving objects where you've got very little friction, you would have a near elastic collision. Finally, let's look at explosive collisions. So let's think about a system which is this little thing here, and you've got, this is mass 4 kilograms, this is mass 1.5 kilograms, and the velocity is 0. And this is before and after. This here has like a little piston that explodes, and it causes the two trolleys to decouple and go their merry ways. And so we've got this kind of explosion here that makes that happen. So this is still 4 kilograms. Oops. This is 1.5 kilograms. And this velocity here is 5 meters per second, and we want to find out what this velocity is. Oops, not 0. So the momentum at the beginning is 0 because there's no motion. So the momentum of this trolley is mv is going to be 4 times 5 is going to be 20. Well, be minus 20, sorry, because let's make that a bit clearer. The time's a bit better. So this is going to be minus 5 because it's going in that direction, and that'll be minus 20. So the momentum of this one must be equal to positive 20, because when they add them together they have to be 0. So 20 times 1 point is going to be equal to 1.5 times v, where the velocity is going to be 13.3 meters per second. Now we can look at the kinetic energy. So the kinetic energy here is 0. It's obvious. And the kinetic energy of this one, this trolley, is going to be half times the mass, which is 4, times the velocity, which is 5 squared, which gives us 50 joules. And the kinetic energy of this trolley is again half times the mass, 1.5, times 13.3 squared, and that gives us 130 joules. So the total kinetic energy is 180 joules. So in the explosive example, the kinetic energy is not conserved. The total energy is, so if this was a wee explosion here, you would have potential and chemical potential energy stored up in this little pistony thing here, and that explodes and it's still turned into kinetic energy. You may have a spring, but you could have two objects coming together with a spring and they bounce apart. In that situation, you will have energy stored in the spring in the form of potential energy, and that's then transferred into kinetic energy. Similarly, if you had an explosion in the chemicals that cause the explosion, you've got that chemical energy stored that is then turned into kinetic energy. Let's look at one more example. So an electrical power worker needs to fire a length of cable across a river. A cable is attached to the projectile and fired across. The cable and casing have mass 1.2 kilograms, and they leave a launcher at 45 meters per second. The worker and launcher have combined mass of 95 kilograms. Calculate, that's not useful, calculate the velocity of the recoil. So you've got the man and this launcher thing, I'll just draw a gun, and this thing that he's going to fire off. This is before, and before you've got momentum is 0 and kinetic energy is 0. After, we have the cable and this projectile thing going at 45 meters per second, and they have a combined mass of 1.2 kilograms. And you've got the man and his little gun thing, and there'll be a slight recoil, which is the velocity we want, and their mass is 95 kilograms. So the momentum of the projectile and the cable is P equals mv. The mass is 1.2 and the velocity is 45. So their combined momentum, their momentum is 54 kilograms meters per second. Now, because the momentum before is 0, the momentum of the worker and the launcher must be equal to minus 54 kilograms meters squared, which is the mass, which is 95, times the velocity, and therefore the velocity must be 0.57 meters per second, and that is the recoil velocity. So I hope that helps.